Good afternoon, class. Today we'll be looking at lesson 5.3, radical equations.
Ricky, get out of here. Jeez. Kids these days. You can't trust them. Alright, so today we will be studying 5.3, radical equations and expressions. So we'll start off by just simplifying some of these radicals. This is a warm-up. This is a review from 5.1 and 5.2. So the negative of a radical, the negative has to stay outside the radical. And 147, now think of any numbers that are perfect squares that can come out of 147. So just start testing a bunch. They may not be easy to find because 147 is kind of a weird number, but try dividing it by random perfect squares that you know. It won't divide by anything even, so don't bother trying any of the even perfect squares, but you can try 9 because it's a perfect square, so 147 divided by 9. Nope, doesn't work. 25 won't work. 36 won't work. 49 is a perfect square of 7, so try 49. And there you go, 147 divided by 49 is 3. So 147 can be written as 49 times 3. And then 49 is a perfect square, which is why we chose it, so we can remove it from the root sign and it becomes negative 7 root 3. And you're done. Alright, so this next one, underneath the radical sign, we can rewrite this as the negative of 2 to the power of 6 times a cubed times a squared. The reason I chose a cubed and a squared is that the cubed root of a cubed is a, so we'll be able to take this thing out perfectly. And the negative sign we're going to leave in here and just write it as 2 to the power of 6 and then the negative version of that. So the cubed root of 2 to the 6, two groups of 3 2's can come out. So 2 cubed is in here twice, so it can come out as 2 squared, and then the cubed root of a cubed is a, and left underneath the radical will be the negative sign and the a squared. And then of course 2 squared can be rewritten as 4, and it's 4a, and these are cubed roots, times the cubed root of negative a squared. The next one, you can bust this quotient down into 2 distinct radicals. Try to take out multiples of something that is perfect square. 16 will come out of 96, so 96 divided by 16 will give you 6. So 96 can be written as the root of 16 times 6. 75 can be written as the root of 25 times 3. Alright, so the root of 16 is 4, so that's 4 root 6 on top. The root of 25 is 5, so that's 5 root 3 in the denominator. And of course, since these have the same radical index, you can actually divide these roots. And you can write this as 4/5 times root 6 over root 3, which is root 2. Finally, the square root of all this stuff, 68, can be written 68 divided by 4 gives you 17. Okay, so 68 can be written as 4 times 17. A cubed can be written as a squared times a. And b to the 4 can be written as 2 groups of b squared if you want. So we can take the square root of 4 and it gives us 2. We can take the square root of a squared and it gives us a. We can take the square root of b squared, and it gives us b. We take the square root of another b squared, and it gives us another b. So that becomes b squared there. And then all that's left on the inside, we've got rid of all those, is 17a. And you're done. Alright, equations. We'll start off with some really simple ones. Now, x right now is rooted, and we don't want to know root x, we want to know x. So we always have to do the opposite. So you take the root x and you square it. If you square one side, you have to square the other side. Always do the same thing. So we get x on the left, and 4 squared is 16 on the right, and you're done. Same thing here. Square it, x equals 121. Again, square, and x equals, now when you square a fraction, you square the numerator and you square the denominator both independently. So 3/5 squared is 9 over 25. And then again here, square and square, and we get x, and of course, -6 times -6, two negatives will make a positive, and your answer is positive 36. And we're done. Okay, so hit pause, take your time, give this a little read. This is what we're going to be doing today. Page 295 will help you answer these blanks. So, hit pause, go back, fill them in, and then move on to the next page. So here's example 1. Solve an equation with one radical term. And then state the restrictions on x. So, when we have something like this, A is just state the restrictions. The only restriction is that we can't take the root of a negative number. So, this, under the radical sign, your entire radicand has to always be greater than or equal to 0. It can't be negative, but it could be 0, and it could be any number greater than 0. And then just solve this. So 2x must be greater than 1. And then divide each side by 2. X must be greater than 1/2. So this is the only restriction. You cannot choose a value for x that is smaller than 0.5. Now we're going to solve this thing. So the steps, basically, you always want to isolate the radicand as soon as you possibly can. So right now this radicand is attached to the 5 by addition. So we're going to subtract 5 from each side, and it will disappear here. And of course the side will end up being 12 minus 5, which is 7. So you get the root of 2x minus 1 equals 7. Now again, anytime you have the square root of something, you want to square it to get rid of that radical. So we square both sides. The radical disappears. We're just left with 2x minus 1. And on the right side, 7 squared is 49. Then we add 1, 2x equals 50. And then divide by 2, and x equals 25. Alright, so here's the your turn. Take your time, go through it, hit pause. I will show you the worked solution when you unpause it. Alright, so here's your worked solution for the your turn. Hit pause, check over your work, make sure you've done it right. If you didn't, find your mistakes. Alright, so example 2, radical equation with an extraneous root. So hopefully you found the definition of this when you were going through the earlier part of this. So what are the restrictions on n if the equation involves real numbers only? So the radicand, which is just 5 minus n, has to be greater than or equal to 0. So 5 must be greater than or equal to n. Or written another way, n must be less than or equal to 5. So n can go up to 5, but it has to be 5 or smaller, and negatives are okay, because if you subtract a negative n, you're adding it and you get a positive number here. So it doesn't matter that there's an n here as well. We only need to worry about the restrictions on this n, because the only thing we're not allowed to do is take the root of a negative. We can do anything we want with this n, This could be 30. This could be negative 30. Could be negative 4,612. Doesn't matter. But for this to be real, this condition has to exist and must be smaller than or equal to 5. Now let's solve the equation. So again, let's isolate the radical. I'm going to move it over to the other side and make it positive. And I'm going to move the 7 over here and make it positive. So we get n plus 7 equals root 5 minus n. Now again, to get rid of this, you square both sides. Now be careful, and I want you to pay attention here because I know I'm going to see it when you guys start working on these alone. This is not n squared plus 49. This you have to FOIL. N plus 7 squared is n plus 7 times n plus 7. Okay? And that will leave you with n squared plus 14n plus 49. So if you just square each term individually, you will be missing this very important linear term. So we get n squared plus 14n plus 49 equals 5 minus n. So let's bump everything over to one side now, set it equal to 0 and solve. So n squared, we're going to add an n here, so add an n here. So we get plus 15n. We'll subtract a 5, subtract a 5. So plus 44 equals 0. And then you can go ahead and solve this quadratic. So the factors of 44, 11 and 4 will work. So n plus 11 times n plus 4 equals 0. N equals negative 11. N equals negative 4. Okay? These are our two possible solutions. As long as they both comply with this, and they must also both satisfy the original equation, which we'll test right now. Now, these seem like perfectly acceptable solutions, but we have to make sure that they actually satisfy the original equation, because sometimes when we square something, it gives us an unexpected result, and we end up with a root that actually doesn't work. So let's look at n equals negative 4 first. And our original equation here is n minus the root of 5 minus n equals negative 7. So let's test n equals negative 4. So negative 4 minus the root of 5 minus negative 4, which is plus 4, equals negative 7. Negative 4 minus root 9 equals negative 7. Negative 4 minus 3 equals negative 7. Negative 7 equals negative 7. That one's perfect. 4 definitely works. Now let's try 11. Sorry, negative 11. Negative 11 minus the root of 5 minus negative 11 equals negative 7. Negative 11 minus the root of 5 plus 11 is 16. It's supposed to equal negative 7. Negative 11 minus root of 16 is 4 equals negative 7. And here we end up with negative 15 equals negative 7. So this is clearly not true. So then we have to reject that answer. And the only answer is n equals negative 4. Here's your turn. Hit pause, do it. You'll see the solution when you get back. Alright, so here's your solution. Hit pause, take your time, check it out. 3 we have to reject as an answer. 11 we can accept. There you go. That's it for this lesson. See you in class tomorrow.